All right, welcome to an unusual Wednesday edition of ICLR's Friday Forum. Today is August the 6th, 2025. This is the 232nd Friday Forum in the series. The series is hosted by ICLR, the Institute for Catastrophic Loss Reduction. We're Canada's leading source for disaster resilience knowledge. Our mission is to make Canada more resilient to natural disasters. Each month, we present recent research related to that mission. I'm your host, ICLR Chief Engineer, Dr. Keith Porter. I'm speaking to you from London, Ontario. This place is on the traditional lands of the Anishinaabe, Haudenosaunee, Lenape, and Arawandran nations. Last month, you heard from ICLR staff members Dan Sandink and Tamara Mosqueda. They told us about ICLR's Resilient Homes Task Force. That's a collaboration with builders and insurers to find ways to build beyond the building code. It was a great webinar. I very much enjoyed it. If you missed it, check out the recording. You can find the recording, the speaker's deck, and a transcript at www.iclr.org/workshops. You can find all our other Friday Fora there too. Next month, CAL FIRE Deputy Director Frank Bigelow will talk about California's adoption of the Wildland Urban Interface Code and California's recently released fire hazard severity zone maps. If WUI fire, hazard maps, or building codes interest you, join us next month. So why, again, are we having a Friday forum on a late Wednesday afternoon? Because our speakers come from Melbourne and Sydney, Australia, where it is now 6 a.m. Our usual time would have had them up at 3 a.m. on Saturday morning. It's still early, but it's not 3 a.m. Saturday early. Our speakers are Dr. Josh Soderholm, Dr. Luis Ackermann, and Dr. Rhys Whitley. Josh and Luis are atmospheric scientists with the Australia Bureau of Meteorology. They work in radar science and they focus on hail. Rhys is an environmental scientist. He makes loss models at Suncorp, a large Australian general insurer. Their topic today is estimating hail damage using radar data. Australia has bigger hail problems than Canada, at least by a couple of measures. Canada has had 2 $1 billion or greater hailstorms. Australia has had 11. Our largest hailstorm cost $3 billion. The 1999 Eastern Sydney hailstorm cost about $8 billion in Canadian dollars. And Australia's population is about 2/3 that of Canada. I'm looking forward to hearing about how estimating hail losses is going to help Australians improve their resilience. I also want to see the alignment of insurer and government interests in hail loss estimation, and I'm going to pay attention to what comes next for this model. Now, before our speakers begin, here's our agenda. Our webinar is going to last 90 minutes. Our speakers will present for about half of that. Then I'm going to moderate Q&A for the rest of the time. Please feel free to chat your questions into the Q&A box. I'll try to pose your questions in the order they appear in the Q&A box. If we have a lot of questions, I may only pose your first question, then I'll move on to others, then I'll circle back to your additional questions. Our webinar is recorded, and ICLR will post our speakers' slides and a link to the video in the next few days. If you have colleagues who couldn't attend, let them know. You can find the video and the deck and the transcript and etc. at www.iclr.org/workshops, probably around Monday. And now I will turn it over to our speakers. Gentlemen, take it away.
Well, thank you, Keith, for that introduction, and it's great to be here. So from the introduction, my name is Rhys, and I'm the principal scientist for the natural perils team that forms our pricing analytics division at Suncorp's consumer insurance space. I'm part of a team that's quite diverse. We're made up of actuaries, climate scientists, engineers, computer scientists, and we're dedicated to determining the risk cost of all the natural hazards that affect Australian home and motor owners across the country. I like to think we're quite cutting edge in our team. We take the best available science for each peril and use it to form accurate and fair premiums for our customers. using the latest statistical and machine learning techniques. We don't rely on one source of data. We try to seek out all sources of truth to get the best view possible. And when we don't see it exist, we go and fund the closure of those knowledge gaps, which leads us to today's talk, which Luis will give the bulk of. And I'm just going to provide some context on why we've embarked on this partnership between a general insurer and a weather agency, and how our knowledge of severe thunderstorms is quite limited despite the scale of damage and our exposure to them. So severe convective storms represent one of the most financially destructive natural perils that we cover for in Australia. And that's across multiple lines of business, particularly in residential property. Hailstorms systematically destroy a lot of the home structure, roofing materials, windows, skylights, solar panels, etc., and cause quite excessive water damage through compromised building envelope. So you can see from these photos, all those tarpaulins there on the left, that is from the 1999 Sydney hailstorm. And there in the top right, and I guess on the top, you can see that the penetration is quite significant. And when you get that water into the building, the damage, particularly in aggregate, can be quite large. Also, there's the motor vehicle component attached to this peril. Vehicles can be damaged in tens of thousands in just a single afternoon. And you're looking at $5,000 to $10,000 on average in terms of claims costs, if not a total write-off. There's also other damage we don't really insure for, but we're quite cognizant of it, particularly with airlines. I think that's from a Turkish airline, but I know for the Sydney 99 hailstorm, a lot of aircraft were damaged. And I guess something with hail is that the lead time or the warnings for such events is very small, that it's very hard for customers or anyone to react to get things out of harm's way. And of course, there's agriculture, which we don't cover, but there's also a significant hazard to that industry. So this is the, when we look at insurance impacts for severe thunderstorms, hail, it ranks as one of the costliest natural hazards that can affect Australians. So these numbers are taken from the Insurance Council of Australia's Natural Catastrophes database. And we've got historical losses here that are normalised to 2022, which considers all the economic inflation, cost of construction, and population growth and expansion. What I wanted to highlight is, while incredibly rare, hailstorms are quite dominant events in the historical record, and can easily reach up to and exceed $1 billion in losses. And in fact, that 99 hailstorm is ranked as one of the most destructive events for Australia since records began since 1967. And as Keith mentioned, it equates to about close to 9 billion Australian dollars, just in insured losses alone. The economic losses would be higher. And it's just the scale of the damage from that event. There are over, I think, 25,000 homes affected, or buildings, and up to 70,000 domestic vehicles, and all in one single afternoon. And while this was originally seen as an anomaly, there are indications that this wasn't that exceptional an event. The hail sizes may have been around 7 centimeters. I guess Josh can comment more on that. But what made it destructive was the path it took through Sydney, which is one of the wealthiest parts, the eastern suburbs. And more than anything, it highlighted the exposure a city like Sydney has to severe thunderstorms. So with that in mind, it's not surprising to see that severe thunderstorms and hail can be one of the biggest loss-making perils for any insurer. And this is an example from Suncorp. It takes up quite a significant portion of our natural hazards allowance. If you were to group all the severe thunderstorm impacts into one peril, here we actually separate hail, just the stone, as opposed to the wind, lightning, and rainwater ingress. You would get a lot of that storm proportion together with the hail one, and it would overwhelmingly make up at least 50% across all lines of business. And the reason for these large proportions is that while the average claim size may be smaller when you compare it to other perils like flood and bushfire, where you would get a total loss on the home. Severe thunderstorms across Australia do affect these large population centres. So it's a concentration risk as opposed to this location risk that you see with other perils. Consequently, event loss totals in aggregate can be easily in the hundreds of $millions for us. So additionally, there's also little our customers can do to prepare or mitigate against the damage. These events where we have significant hailfall, highly localized, short-lived, so it's difficult to predict to the point that we can't really offer any lead time for our customers to react. For us at Suncorp, we've had a good but limited view of severe thunderstorm and hail risk across Australia, and we try and ensemble different perspectives of this risk from the market and our research partners. However, while these are highly informative, these views are limited to large-scale geographic views of risk, and refer more to the environment that produced severe thunderstorms rather than the actual severity of the actual storm itself. So we're limited to a very coarse scale view. This is an important point. So while it is useful to identify these storm-prone environments, our inability to reliably predict specific frequency, intensity, and the insurance impact of severe thunderstorms at a more granular level is somewhat detrimental to us for accurate insurance pricing, particularly when we understand more local effects are playing a role on thunderstorm risks at that sub-regional scale. So while we understand how storms are notoriously difficult to observe and model because they are small scale and relatively rare phenomena, as an insurer, we can't afford to price in severe thunderstorm risks based on incomplete science. So it's imperative to our customers and shareholders that we get the fairest and most accurate view of the risk possible. Consequently, we see collaborative research as our path to developing a better view of severe thunderstorm risks across Australia and our understanding of them, and is why Suncorp reached out to Josh and Lewis and others at the Australian Bureau of Meteorology. And on that, I'm happy to pass on to Josh, if that works for you, Josh.
Thanks, Reese. Lewis, can you share your slides now?
Sorry, can you see them?
Yep, they've come up.
Perfect. And just let me know when you want me to switch.
Thank you, Lewis. Okay, next slide. Next slide again. All right, so we just heard from Reese at Suncorp about the general insurer's perspective on why they're interested in investing in a science project with the Bureau of Meteorology. And now I'll give an overview of why the Bureau of Meteorology was very interested in this collaboration with a large general insurer to better understand hail across Australia. So the Bureau of Meteorology itself, just like Environment Canada, it's responsible for Australia's weather forecasts, our severe weather warnings, climate monitoring, and hydrological services. We're there to protect life and property, while also ensuring Australia's economic, environmental, and social needs are met relating to weather and climate services. We also provide specialised data, forecasts, and climate information back out to industry to enable their productivity. So this is including agriculture, aviation, mining, tourism, as some examples. And this weather information we basically designed to allow them to make more informed operational decisions and manage weather-related risk. And of course, insurance falls under this umbrella as well. As part of this introduction, I also want to introduce the radar network in Australia. You can see the map of the current operational sites on the right as of 2025. So we have currently more than 70 radar sites across Australia. A bit like Canada, we have very large areas where there is no coverage, but for us, they're essentially the desert regions where there is very little population. So you can see a majority of our radars are situated along the coast, particularly on the east coast. And this is very important for our our discussion today going forward as well. Next slide, please, Lewis. So these radars are actually sitting along the east coast, and this is coincidentally where we also see a majority of our thunderstorm activity, which is co-located with some of Australia's most densely populated cities. So the map on the left shows a radar-derived severe hail climatology for Australia, where our hotter colours are indicating more frequent severe hailstorms across Australia. You can see the peak activity is centred across the cities of Brisbane and down 1,000 kilometres south to Sydney. So this area, these are two very large cities. Sydney has about 5.7 million people and Brisbane is rapidly approaching 3 million people. So they're significant urban centres in Australia. You can see the map of Australia's population is also very biased to this east coast as well, with the population map on the right. So there is significant interest in better responding to the exposure which we're presented here regarding the hail hazard. The next slide, please, Lewis. The next slide. Another problem for us in Australia is we currently have no ongoing public reporting of thunderstorm hazards, including hail. So for us, this is a big problem when we're trying to find some sort of ground truth to develop new retrievals, new environmental information, and new environmental proxies relating to hail. We do have some historical archives, but the quality is low, and also they're like any report data set, they're affected by the poor spatial coverage, where our reports are biased towards capital cities. So this strongly motivates us to explore alternate data sets to better understand hail risk across Australia and better understand our understanding of hail estimates within the Bureau. So an example of what the data sets we had before this project is on the right here. So on the left, we have all of our hail reports from one of our internal archives plotted up. And you can see they're very biased towards the capital cities of Melbourne, Sydney, and Brisbane. Of course, we do have a lot through that region where we do have hail impacts, but this is across quite a lengthy period as well. So we're talking more than 35 years. So the numbers are actually not that significant per event. We might only have a couple of reports per event, which is really quite insignificant in the scheme of things. And when we look at larger hail sizes as well, which create the more significant impacts, which Reece showed in his slides, the numbers drop off very quickly across Australia, despite these events occurring regularly across the warm season. So there is a strong desire by many of the Bureau's customers, not just insurers, but also by our forecasters who service the general public, by energy and resources, and also by agriculture, to better understand first of all, the risk of hail across Australia, and then have better information when hailstorms are occurring to understand their impact. Next slide, please, Lewis. So this brings us to the last few years. So there's been a renewed focus on hail at the Bureau of Meteorology, and this has included the development of national calibrated hail guidance, where we use our radar network that's been calibrated to map hail in real time and provide retrievals to our forecasters. And this information will also be going out to businesses as well who require it. But this is the baseline information where we're only estimating hail size, but it's a great place to start building upon. We also, as part of this project, developed our long-term calibrated archives of hail estimates from weather radar across Australia. So we essentially reprocessed our radar archives, quality controlled them, and generated our hail retrievals back in the past as well to complement what we're doing for the real-time operations. So our collaboration with Suncorp, we were very excited to hear they're keen to work on similar problems that we are focused on internally at the Bureau. But also bring along their experience, their knowledge, and of course their data sets as well to help fill many of the gaps which we're faced with. So this collaboration, that Lewis will be delivering the research from today, builds upon many of these capabilities we've developed across Suncorp and the Bureau, and enables us to have a new impact-based assessment of property and motor damage that is very relevant, particularly for our insurance industry in Australia. And yep, I'll hand it over to you, Lewis.
All right. And you can hear me well? I cannot see you, so I'm gonna hope that's a yes. Okay,
yeah,
great.
We hear you.
Awesome. So I'm bringing this this figure back just to give you a little bit of reference. During the talk, I'm going to show you some of the products that we're generating, and I'm going to reference these two events that are the one on the left is the 2014 Brisbane one, and that is a little bit more on the expensive side, and the Halloween event on the right. And just to show basically what it looks like, the products that we're generating on events that are somewhat on the high end, but not on the very outlier end. And of course, this is why. And I just wanted to show you a physical example of what we actually see on the ground that are generating those huge damages. So our motivation. A little bit of context before we go forward, just on how we derive one of the measurements that we're going to use a lot and we're going to reference here, which is that severe hail index, SHI. That is basically created by doing an integration of reflectivity above the melting layer. Basically, the radar looks at a thunderstorm, and it will take any measurements above the melting layer where we expect hail to grow, and we integrate that in a weighted manner, and that gives us this severe hail index. That has some information about how much hail there might be on that volume. Now, that's not necessarily the size of the hail. To do that, basically, that severe hail index is fitted to some observed hail sizes on the ground, and we'll show you that later on. So the objective of our project was basically to create an improved radar-derived hail product using our radar archive and leveraging the about 10 years of claims data from hail damage provided by Suncorp as a ground truth, which is extremely valuable for us. So, but there are some challenges. The first one is hail size uncertainty. As I said before, that SHI, that measurement from the radar, can be then fitted to some hail sizes on the ground. And that's the relationship that we observe. The one we're actually using to do that correction is that blue one that was on the 75th percentile. But as you can see, all of those fits are somewhat uncertain. There's a lot of variability. And what we can see in effect is that for the same radar measurement, you can have multiple hail sizes that match to those. And that's due to the fact that for the radar, a volume with a few large hailstones will have the same amount of reflectivity that a volume with a large amount of smaller hailstones. So there is an intrinsic uncertainty on the hail size distribution that the radar cannot decipher, cannot tell. Nevertheless, that's the fitting that we have, and that's basically a radar-derived hail product that is widely used, mesh. The other challenge that there is with using radar to detect hail is that, well, if you use something like mesh, which is derived from SHI, that is derived from observations aloft, above the melting layer, which can be up to 2 kilometers high. But that is within a storm that has some movement because of the winds, the storm winds plus the large-scale winds. And that will create advection, basically a movement of the storm, of the stones from where they were grown and created and detected to where they actually land and create some damage. And here on the right, we can see studies from Brook et al. On 2021, that basically because on that domain, they had a multi-Doppler radar, they can have 3D winds, and then they can actually try to do trajectories for each hailstones and do basically a correction for that storm. And you can see the dots are what the radar detects as potential hail. The blue is the damage on the ground, and you can see that before correction is offset to the right, while after correcting it for wind advection, it's much better represents the damage swath. So that is an actual problem. And in most of our domains, we don't necessarily have a way of creating 3D winds because we don't have multi-Doppler radar coverage. So the first part I'm going to show you on the results is going to be on the residential hail damage estimates, for which we use the data set that Suncorp provided for hail damage on houses. And then once we started looking at the data, we quickly realized that there was a source of variability that we needed to correct for, and that was the vulnerability differences between different property types. And here's a good point to remind everybody that we actually got a policy level data from Suncorp, meaning that we had not only claims, we also had nulls, which was extremely important to basically know where there were no claims also. But we also had characteristics for each one of the policies. So roof type, wall type, tree coverage, the year of build, etc. And what we find is that if we combine these characteristics into basically archetypes, we saw that basically houses with tiles and concrete walls were fairly common, and we can group them. Tiles, houses with metal roofs and wood walls were fairly common. So we were able to create some archetypes that represented most of the data. 11 archetypes represented more than 85% of the data. And we created a last archetype, number 12 there, that basically grabbed everything else, houses that were very uncommon. And what you can see there is the distribution of the relative damage. And by relative damage, I mean the incurred loss divided by the insured sum. So I'm going to be using damage referencing to that in general. And we can see that there's a lot of variability or different vulnerability for each one of those archetypical property types. And before we go forward, we need to basically correct for that, because otherwise we're trying to the vulnerability due to the intrinsic house properties has nothing to do with the hail itself. So we needed to correct for that to create a normalized damage. So what we did is basically we took the median for each one of those archetypes and we corrected it so each archetype has the median hail relative damage equal to the overall data set, which is the column on the right. So that allows us to basically group them, compare apples to apples. The other issue that we needed to fix first is that, well, we needed to have a good data set that where we were sure there were significant hail damage that we can then compare to the radar. You can see the original data set on the left that basically there's a characteristics hail swath, the damages on red, but there were areas where they were uncertain whether or not the damage was significant. So what we tried to do is we kept policies or grid points that where we had a majority of damage, and then grid points where we had basically no damage, and anywhere in between where the damage would have been uncertain or difficult to pinpoint, we maxed them out. And then we gridded the data, and since we already had corrected for vulnerability differences, we can actually grid data and have an average damage per grid point. And we did this for all the events. We had a little bit less than 30 events, 30 intense hail events, where we were working from many cities, but overwhelmingly from the East Coast. So what we did with the advection problem, since we cannot rely on having 3D winds for everywhere, we needed to look for another solution. And what we came from this assumption of, well, let's say the radar observations are not perfect. We saw that that fit is not great, but there is information there. Let's assume for a second that the radar do have some information about how much hail there is. Maybe it's not correct, but potentially for each event, it has a relative scale, meaning that if you have some detections of hail above that is very intense, and you have some place on the bottom where you have a hotspot, most likely the hotspot is due to the hotspot on the radar observation. And that's what we did. We basically took all the grid points for each event. We sorted them from descending order, starting from the highest point of damage, and we look on a 4-kilometer radius of influence, the highest radar signature close to it, and we match them. We're saying, well, the highest damage should be due to the highest radar signature close to it. And then we to the next grid point and find the next radar point and match them together. And you can see on the left-hand side are before any correction, any advection correction. The right-hand side is if we match all of them, basically that star represents the average of all of the corrections. You can see them all were basically to the left. And if we apply that bulk correction into the radar data set, we can see that then the swath actually matches quite well. So this is, if we have claims on the bottom, this is basically a way of correcting for that advection, which is what we did for all events, and we basically corrected that. And now that created a data set of ground damages that was matched to radar observations aloft. And with that, we can see a little bit of the progression. So this is the start of the project, the relationship between mesh, so radar, and observed damage without correcting for advection, as you can see, quite bad. And I will explain what the blue and red means. If we correct for advection, it improves, but still not great. And you can see that fit on that grid line. That grid line is a sigmoid. You can see that, well, the fit is not terrible, but it's not great for sure. But one of the things that we saw is that the blue and the red there are two specific events, 2 days, those days that we have been talking about. And the black is all of the other ones. And you can see, and this, we saw it over and over, event-wise, there is a somewhat of a relationship. You can see that we can potentially move that green fitted line to match that single event. But of course, it wouldn't match the other ones. Then that red one could potentially be fitted individually. So this gave us some hope that, well, the radar is indeed picking up something correctly within the event. The problem is that there are changes from one event to another one that the radar is not picking up that are driving a lot of that variability potentially. And what we tried is, well, say, well, maybe there's something in the meteorology that we can use to fix that. And we try multiple equations and formulas and corrections, but it ended up being not that straightforward. But we found out that if we use a neural network and we basically use a lot of meteorological variables from ERA5 for the location, for the time of the event, we can actually correct for that. And that's what we did. And this is that new hail damage estimate model, which is basically a radar plus meteorology product that corrects a lot of the variability that we were seeing, creating a very nice correlation. If we see what it ended up driving the model, and the way we did it is we created this model, we put as much from the meteorological science as we can think of using ERA that potentially could be an effect, and then use CHAP analysis, which basically tells you how much each input variable has an impact on the output, and started removing input variables that had basically no impact, and rerunning the model and removing variables that were not really impactful until we ended up with only the really impactful ones. Basically, when we started removing variables and the performance starts to decrease, we stopped. We can see that the variables that survive were on top of everything, the radar, the severe health index, driving about a third of the variability. And then the rest was this other meteorological variables, humidity, winds, and convection variable and convection inhibition variables, which physically makes sense. Now, creating this model with a relatively good performance, I will say, kind of allows the possibility of, since this model is calculated aloft where the SHI is being measured, and mesh is also aloft, this kind of bypasses the problem with the advection. So we can say, well, if we have this HDE, this potential truth for damages, we can then compare it to mesh, since they're both aloft, and see if there's actually some relationship that we can get between mesh, the more traditional radar product, and this new damage that is aloft. And we saw that the fit is actually not bad. There is a lot of variability, as we saw. So in here, we can see that vertical variability that is due to the uncertainty of the hill size distribution, which the radar cannot tell, but at least we have some of a correct of a fit. That red line there, that fit, is that green line. And then using that fit, we can then, from damages, back calculate hill size, which is what we did on panel D here, just so we can have, because damage percentage is a little bit weird for us scientists. We are much more used to hill sizes in our mind as a references for damages.
Sorry,
so
Louis,
yep.
may I interrupt you for just a second? We are seeing a message bar at the bottom of your screen that says Teams is sharing your screen. Yes, thank you so much. Yeah, well, now we're seeing your presenter view.
Yeah, let me see if I can get back to it.
The thing is that message is hiding some of your axis labels, and it's.
Can you see the presentation now?
No, it's gone.
All right, no worries. We'll get it there. Yeah, I was seeing that, but sometimes it's not shown in the actual Teams. So I can hide it, and then I can go back there.
That looks, yeah, thank you so much. That's
all right. We'll get in there real quickly.
Sorry to interrupt.
No, that was perfect, because sometimes those pop-ups don't actually pass through, but you never know. Thanks for that. So yes, so perfect. So back calculating it, we can actually see better the effect of the correction that the meteorology is doing to the radar. And now we can see how those, basically that blue event that was estimated by the radar, basically saying that the hail was of higher damage that we could have expected with respect to the mean of the distribution, was corrected on the right direction, while the red was corrected also in the right direction. So that was quite promising. Now let's see each one of those, the red and the blue, more in a special sense, what actually happened on the ground. On the left here, we have the original mesh from the radar, nothing special, already advection corrected. And you can see that on the bottom here, we have the damage swath on red with the gray where no damage happens. On the middle, we have that back calculated mesh, basically derived from that fit from the model. And we can see that it is a much more tight contours for the damage. One of the things that quickly show up is that anything that didn't produce any damage, that is, we can see here, basically got suppressed by the model. Here I'm showing the difference between the two, where basically blue colors show that the new mesh, the corrected mesh, is lower. So you can see that overall the model is suppressing the signal, not as much in the cores, a lot in the outsides, and you can see that basically result of correcting it. Now for the other event that it actually corrected on the other way, we can see the same effect on the places where no damage occurred, but actually on the actual swath, it was actually enhancing it, which is what we needed to happen. So we can see that it's not just doing it across the board for each event. It's dependent on the actual location, potentially being driven by the radar observation. Another nice thing to note here is that you might have noticed that, well, this damage reports were actually corrected to 0. What's up with that? And those reports are actually from this location. That I actually went ahead and looked why are they being corrected to 0, and look around from satellite images and actual radar observations, and there were basically no clouds ever reaching that area. So those are pretty much spurious or mistakes on the data set, or maybe other damage that were mislabeled. So the model actually was able to identify mislabel or no damages and corrected for those, which was interesting. So now let's jump to the vehicular hail damage estimate. And the idea here was, well, we did this with residents. Can we do the same with vehicles and have an estimate of damage from radar, potentially corrected with metrology for vehicles? The first challenge that we saw is that, well, we needed to do the vulnerability correction as we did for the archetypes on the houses. But for vehicles, there is a lot more archetypes. You have much more different makes. We had all the information, and basically we didn't find that the size of the engine really mattered on hail damage, as you might have expected. But there were still a lot of things that mattered. The make was very important. The type of use of the vehicle, if it was a private, a commercial, or something like rideshare, did have an effect. The body type, the decade of manufacture, those things had an effect on the vulnerability. And then when you combine all the possible combinations of those, we find that we had something like 10,000 different archetypes or different combinations. So how do we deal with that? Well, one of the things that I'm showing here is basically policies per archetype. So you can see that there's some very common cars, maybe something like a Corolla, while then you have things that are more rare, like your luxury cars. The other part is, well, in red you have policies. Each one of those dots is a different archetype of vehicles. You have archetypes that produce a lot of policies, mostly driven by the popularity. So there's a relationship. But we realized that, well, if we had an archetype that has less than 30 policies, we cannot really say anything statistically significant about the distribution of their damage, right? So we basically filtered any archetype and policy and types of cars that had less than 30 policy or 30 claims in the data set. We just grouped them into one bucket, like we did with the houses on that 12th. And we're calling it the other archetype. And that's about 18% of the data. 81% of the data is represented by specific archetypes, which turn out to be about only 400 archetypes, which is much more manageable than 10,000. If we see the variability of the damage ratio of each one of those archetypes, and I'm just showing the median, the mean and the 25 and 75 percentile, with this one being the other bucket, that 18%, we can see that there's a lot of variability. So we needed to correct for that vulnerability differences. And we did the same thing that we did with the houses, basically where we made it such that the mean damage ratio for each archetype was equal to the overall mean damage ratio. That way we can have apples and apples. Now, the second big challenge with the vehicles is that we don't know where they are when they got damaged. From the policy data, we only had the address of the residents associated with that policy, the postal residency. Not the data set didn't contain the location where the hail damage occurred, which is understandable, but it brings a big issue, kind of like the advection problem. We don't know what to match to what. The advection side, since we're using the same event data set, we actually cheated, and we used the correction that we already calculated from the advection, the bulk advection for the houses. Since we know they're the same events, we know that they moved this much. So at least the advection part, we can cheat and use the house correction. But how do we know where the car was? Well, we started with the following assumption. Well, let's say if you have a small neighborhood, like 1 kilometer square neighborhood, and you have a bunch of policies associated with that neighborhood. The likelihood that those policies happen because the cars all move around, commuted, whatever, and they were all at the same spot where the storm happened is low, that they all happen to be there by coincidence. It is more likely that they were damaged close by to that policy, and therefore that's why you have a hotspot in that area. So that's what I'm showing here. All those panels show basically, and I'm going to start basically on the left. If I were to filter policies by the amount of policies that they have close by, so basically if I had just one hit within 1 kilometer or 2 hits or 3 hits, I can potentially filter out cars that were not close to the storm that just happened to be hit by it. So let's say, and in blue here we have the swath of the damage for this event. We can see that there were some cars here that are not associated with any of the swath of the event, so are likely just commuted and got hit by it. But there's definitely a hotspot in that is associated with the swath. If we increase that number of policies that reported claims that are needed per that small neighborhood, 1 kilometer square, we can see that if we go all the way to 10, then that signature in red very closely matches our swath. We lose a lot of the data, right, from 8,000 to 6,000, but we basically know that the ones that are being left are, at least we can associate it or match it to their respective radar signature. Now that's for that event, but we saw, well, other events are a little bit different. If we use such a high threshold for hits, then we lose a lot of the data. We go from 1,600 to a little bit less than 500. So we basically find that, well, somewhere in the middle of that, about 5 hits provides a good in-between that works for most events, where you keep as much as the data you can. I'm going just back, but you don't have, you at least remove the clear outliers that were just, they were nowhere close to any storm. And then once we had that, what we did is, well, now we have cars that are unlikely being damaged right on their house where they were parked, but at least in the vicinity. And then we can do the same kind of assumption to match it to radar observations that we did for the houses, basically where we look for the highest damage and we match it to the highest radar damage. But here we're not gridding the vehicles, the cars, because we cannot really grid them, because we don't know that they were actually in the same grid point. Our grid points from the radar are 1 kilometer by 1 kilometer. So what we did is policy-wise, we matched to radar by policy. But that brings the problem of, well, how many policies do I match to a single radar point? So we needed to know basically how much space each grid point could have potentially hold in cars. We went to Google Maps and basically got information about the road sizes and types for the whole domain, gridded that to the same radar grid to create an estimate of how many cars can each radar grid hold potentially. And that allows us to basically say, okay, so this radar grid that has this amount of hail potentially can potentially hold this many cars around it. And then we match policies that were already filtered for definitely cars that were too far from their location to a radar grids based on this maximum amount of vehicles that could be held by it. And that created a matched data set of damage to radar observations. And we apply the same methodology where we use meteorological variables to correct, and we were able to basically create this new HDE for vehicles. With a similar, not as good as a performance as the houses, likely due to the uncertainties on the movement of the vehicles. And it was especially hard to predict the really high damages, mostly because it's not as represented on the data set, so it's hard for the model to actually predict it, although we did try some weighings on the training. But nevertheless, a relatively good performance. I'm just showing you there, we needed one more meteorological variable, but the meteorological variables for vehicles were not the same as for houses. And this is likely due to your being on a different size of the sensitivity. Basically, we needed to be able to discern smaller hailstones, because smaller hailstones that will not damage houses will still damage cars, which is part of the importance of this research. It allows us to bridge that gap into less severe hail, but still damaging. Now, if we use this data set of vehicles now that we have and we run it for the whole archive for one of the domains, we can create, we can see, well, every time it exceeds a certain threshold where we know damage is going to then be recorded on the ground, we can then create climatologies. And this is the climatology for Brisbane, for example, for hail damage. Basically, how many times it is likely or expected to have some damage for vehicles. And we can see that then some spatial biases start to show up. So there are some definitely hotspots that are present. If we want to see, well, how is this changing over time? One of the things that we really want to know is, well, not only are damages more common or not, something that comes up often in the literature is that, well, it might be that maybe the overall frequency of hailstorms is decreasing or increasing depending on climate change, but maybe the intensity is changing. So maybe they're less frequent but more intense, or more frequent but less intense, depending on the place. So what we did is we defined this as thresholds for exceedances, and we tried to see if there's any statistically significant trends on any of those thresholds. So we can see, well, are the frequency decreasing overall, or whether or not some intensities frequencies are increasing. So we can see, for example, for Brisbane, none of those different thresholds are showing any statistically significant trends. While if we go for for another domain like Melbourne, where we see overall less hail frequency, but we see changes on some of those intensities. So we can see that the low intensity damages pretty much show no statistical significant change or trends, but on the higher, on the lower ends of the intensity, there is an increase, statistically significant increasing trend. On another location, Perth, we see a different situation happening, where we see pretty much all intensities showing a decreasing trend for that data set, statistically significant decreasing trends. Now, if we compare, now that we have both products, if we try to use them to have some comparisons, first, as a sanity check, does it make sense what we're seeing? So in a sense, we shouldn't see that we have a place from a storm, the same storm, where we have vehicular damage and no, but the other way around, where we have damage on houses, so very intense hail, that is not damaging cars, right? It makes no sense. We should see it the other way around. We should see places where you have hail damage for houses and cars, and then some places where only cars got damaged because the hail was less intense, and we see it here. Now, surprisingly, I would have expected a priori that there will be a bigger like footprint around that, so it will be a little more of a smooth transition between no stones and big stones able to damage houses. But what we saw is that solar storms just have cores that are showing very sharp edges with no smooth decreasing on hail sizes. On the other hand, some storms do show some, so this one, you can see some damages on places where there were no residential damages, while others basically have almost full association where there's damages for both of them and basically no damage for only one of them. If we do a more statistical analysis, we can see the likelihood of annual risk for hail for vehicles and residential, and we can see, well, what we expected. Vehicles are much more likely to be damaged than houses, although they share somewhat the same hotspots. If we go for another domain where hail is not only less frequent, but in general less intense, we can see that there's stark differences between the residential risk and the vehicular risk, which shows the value of having repeated that methodology for the vehicles. And summary, basically, that we can potentially leave there for people to observe during the questions.
Wonderful. Thank you so much. Give people a second to absorb the summary that's on the screen as I look over my questions. We don't have any questions yet from attendees. So let me ask some of mine. Gentlemen, Joshua posted a link to a 2024 paper. Is that report, is that clear enough that, you know, and that people could imitate it in Canada? And I'm thinking, you know, are the data, that also begs the question of whether the meteorological data and the policy data that you have available to you in Australia, is that kind of information generally available in Canada as well? So in other words, is this something that we could imitate in Canada?
Well, on the meteorological side, yes, definitely. We use R5, which is a widely available data set. It's an hourly data set, and we use it. Basically, we find the closest grid point from R5 that were collocated to the radar, and the closest hour to each one of the radar observations. On the policy side, I will say most likely, that's not my field, but I will guess that the insurance will keep track of which policies were associated with hail or other perils, so they can segregate them from that. And keeping track of the properties on the policies is probably something that you do regardless, to know their potential vulnerability. So I will say definitely something that you should be able to do, but I don't know what you guys think.
And I'll just highlight that the Northern Hail Project had been working on implementing the radar retrievals that we use as well. So we use a US approach called Mesh, and it's also being implemented by Environment Canada with collaboration with the Northern Hail Project. So I believe lots of the underlying data is there. It might need a little bit more work to get to the point, but there's definitely huge potential to repeat a similar type of analysis.
Mark Baker, I'm going to ask you to chat your question into the Q&A box. We don't unmute you just because of this format. Thank you very much. So those 6 parameters that the AI picked out, the 6 impactful variables, those are standard meteorological parameters that Environment and Climate Change Canada would normally be collecting and disseminating?
Yeah. So that ERA5 product is a global product. It provides coverage everywhere.
Cool. Let's see. Your slide 16 with the box and whiskers, I didn't quite pick up on that when you said that you sort of normalize the vulnerability of the archetypes to the overall average. Are you saying that you sort of have a single vulnerability function that you then just sort of scale up or down uniformly depending on which archetype a building falls into?
Yeah, basically, given using the medium of the distribution for each archetype, I basically corrected such that the new medium of that archetype will be equal to the overall medium hail damage. I could have put it anywhere. It's just that keeping it at that point allows us to be a little more sensible. Anyway, once you calculate HDE, when Suncorp wants to use that value to calculate the actual incurred costs that they will experience, they have a vulnerability curve associated with that correction. So HDE will then go through that vulnerability curve for that archetype, for that policy, that then will translate that HDE into percentage damage for that property, that then they can multiply by the insured sum to get the estimated cost for that policy, for that event. So we had basically 12 vulnerability curve that each one associated with one archetype.
I see.
And for the same for the vehicles, but we just had 400 of them.
I see. And the residential property one, the one that Joshua linked a paper to, that has the 12 vulnerability functions in it, or does that has the 412?
No, so that paper is for the residential properties. That one doesn't. The vulnerability curve were not shared publicly for commercial reasons. Because
okay.
that yeah.
I mean, they probably wouldn't be very useful overseas either. They're all going to be relevant for Eastern Australia or wherever we hold policies. But the idea of the paper was you could repeat the experiment to derive your own vulnerability curves if you were another insurer interested in this work.
Gotcha. Okay, so the archetype specific vulnerability curves are proprietary, right?
Yes, because they will be linked. They're calibrated to our insurance claims.
Gotcha.
Yep.
Okay. Thanks. Reese, can you tell me how are you using that model in practice? How is the use of this model helping you do business? Is it saving you money? Are you doing it on claims? How does this inject into your sort of daily business practice?
Yeah, it's a good question. So we use it for pricing. It helps us get to a more granular view of the risks. We like to price at the address level in Australia for all perils. And that works really well when you have something like riverine flood or bushfire or wildfire, I guess, for you guys. With hail, it's not going to be that granular, but we can drill down further as opposed to, I don't know, I think it used to be like 50 or 75 square kilometer. That was the limit of our view. But we can now get to more convective permitting resolution, maybe 5 kilometers, which can make a massive difference for fairer pricing. So there's less cross subsidization for our customer base, at least regionally. So, I mean, that's the short answer. It's just that we get fairer, more accurate pricing to the extent that the data allows us to do this.
Gotcha.
But there is I guess Josh can probably speak to this. We do see other uses for this product. We're going to continue the relationship with the Bureau. We are looking at doing a nowcasting exercise where this product would be used once again. I don't know if you wanted to comment on that, Josh.
Yeah, sure. So this is essentially a radar retrieval, which we're talking about here. We can run it historically, which is what Lewis has presented, or we can run it in real time and produce real-time maps of estimated loss at sort of a 1 kilometer resolution. And we can also produce short-term predictions, say out to 30 minutes, out to 60 minutes, of what the losses might be if the thunderstorm continues on our predicted path. So there are two other applications which we're currently starting up projects to implement. And this will essentially allow for better earlier response by insurers as they plan for these events as they're occurring and respond to them, to the benefit of customers, of course, as I'm sure Reese can comment more on.
Yeah, we do try and issue warnings to the customers when we get and guidance from the Bureau for one, and I think some other partners. But the best we can do is probably 30 minutes if we're lucky. It is hard. The thunderstorms will hit at the worst time of the day, usually the peak hour. Typically when everyone's car's out, they're either they're coming home from work, or they're picking up the kids from school, and it's when you've probably got the highest density of cars on the road. And so these warnings, they're going to have a limit to what you can do to mitigate possible damage. However, you had longer lead times and understood the severity you're facing, because you don't want to cause panic either, of course. People could probably prepare what they're going to do for the next hour. Maybe I won't take my car out for whatever. I'll delay my trip. It kind of trying to help change the behavior so that the person's not exposed to the storm. I mean, you're not really going to lose your life, but you could if there's a flash flood event, I suppose. But the idea is that we're better informed, and then if we can get these warnings out much earlier, and maybe update them at a higher frequency to the public, then we can do our best to mitigate the impacts of these events.
And is it possible to sort of spatially target the warnings? Do you sort of broadcast a warning that says, look out for hail in these particular locations? You narrow the warnings to just those locations, or how do you optimize that warning? How do you apply the warning message so that, the people who need to see it, and people who don't get bothered by it?
Yeah, it's a good question. So at the moment, it's very broad, the warning. I guess, Josh, you want to mention the AI guidance? It's probably the answer to this.
Yeah. There's a couple of questions there, like around warning communication, but also the resolution of the warning itself. So our warning system is quite similar to Canada at the moment. We use fairly large polygons to represent the expected impact area, but we are moving towards providing more refined spatial mapping of where the storms have been and where they're expected to go, and also breaking these down into individual hazards. So we'll be able to show this storm is having a certain percentage chance of producing severe hail, and a different percentage of wind, a different percentage of rain, heavy rain as well. So breaking the hazards down will allow people to respond more effectively.
Well, you just muted yourself, Joshua.
Oh, sorry. Yeah, so communication is also a huge problem as well. We don't actively disseminate warnings over the cell phone networks in Australia like you guys do in Canada and the US. Instead, we rely on more traditional means, so people accessing the website, the app, through radio, through TV. So that's certainly something that should be looked at, but I can't quite comment on. The other aspect I wanted to comment on is also having better warnings also improves the responsiveness of, say, the insurer who needs to prepare some resources on their end to respond to the event, but also for energy as well, as they need to get their staffing out to respond to damage across the electricity networks, and various other industries as well, which respond to these events. So better warnings do allow for better preparation and faster response across a number of different groups.
Sorry, go ahead.
On the application side, there's one thing that I wanted to mention, something that has been coming up for dealerships is a potential very valuable product that can potentially be done in partnership with the insurance company of the dealership, because one of the things that we have been communicated on is that the dealerships usually have a subset of vehicles that will drive the losses of the lot. And then if they have a warning of 30 minutes, and because the swath are relatively not tremendously huge in area, the dealership can potentially move the highest cost vehicles, the ones that are the biggest loss, out of the way or into the warehouse, and at least mitigate the cost of a potential hailstorm that is coming. So that's I just remember that's one of the talks that we have had internally.
We have a question from Evan Yaton. We have an insurer-funded hail suppression program in Alberta that performs cloud seeding to reduce the intensity of hail. He's interested to know if Australia is doing hail seeding as well.
So we have no systematic program at a federal or state level. There has been a couple intermittent programs at the local government level, but nothing sustained. And I think that really does reflect the science around it. There is still a lot of uncertainty about the cost versus benefit, particularly when you look not just at individual events, but across so many years, many seasons, where is the effect really one to reduce the severity of the hail, or is it sort of lost in the noise? It's something we're still struggling with.
ICLR did some research in the last few years on that question, and we think we do see a signal in the noise of moving the distribution of hailstone sizes to more small stones, and we think the signal is strong enough to be kind of definitive about it. Let's talk a little bit more about those hotspot maps. Do you think that you showed some on slides 34 and 44 in particular? Do you think that those show places that just because of topography or something about I don't know, something that's static on the ground or in nature causes those places to be more frequently hit by big hail, or might those hotspots reflect just sort of randomness that might average out if you were to have more decades of data? Or what do those hotspots actually mean to you physically and sort of in terms of physical processes?
Do you want me to take that one, Lewis?
Sure.
Yeah, so there is across some of the map, there's sort of two kinds of hotspots. There's a sort of more gentle modulation between low peaks and high peaks, which really does reflect the sample size. So particularly for cities which have a low frequency of hailstorms, we see that. For cities with a higher frequency of hailstorms, particularly across the East Coast, and we have very long radar records there as well, we see much less of that behavior. So there we can start to see the true hotspots. And there have been a number of studies, including my own PhD, where I focused on understanding the drivers of those hotspots, and they're really linked to local processes. So we have sea breeze influences across the East Coast, and we have a lot of terrain as well. So we have a mountain range that sits between about 50 and 200 k's inland running down the East Coast. That moderates the initiation of thunderstorms. It also moderates interactions with the sea breeze as well. So that's why you often see on one side of a mountain range a very different thunderstorm climatology compared to the other side of the mountain range across the East Coast. There's a lot of variability across the region.
Mm-hmm. So those hotspots, yeah, I wasn't paying close attention to the scale of those figures, but those figures are.
So for each one of those radar domains, they are the radius is 150 kilometers.
Got it.
Sorry, I forgot to mention that.
Thanks.
And in regards to the effect from topography, from what I remember, we see it also in Canada. I think you have a very clear hotspot that is due to a topographical feature, right, Joshua? This is from a couple of years ago. I remember you had a campaign there.
Yeah, so the Rockies, of course. They drive a lot of what happens across Alberta. Without the Rockies, you would have a completely different thunderstorm climatology across Canada. And of course, across the US as well, without the Rockies, you wouldn't have any of the tornado, nowhere near the magnitude of tornado activity you have across the central plains in the US. So mountains play a huge role no matter where they are.
So if you were to sort of, I'd really love on some other time to see the those hotspots compared with topography or shown with mountain ranges overlain.
Yeah, it's hard to show it in a quantitative way because they are displaced. So it's not that it happens right on top of it. They affect the initiation, and that then downwind affects it. There's another paper that is coming up later this year that talks a lot about the looking at HDE, driving it by HDE. It follows each one of those storms and tracks that object and sees the behavior of that object and the relationship of where is it generated and where the actual damage occurs. So yeah, that basically explains a little bit of why that's that displacement, and also shows biases on direction of initialization, so which way they're usually heading. So, but we didn't include that in this talk.
Keith, I'm really sorry, but I am going to have to drop off to make this workshop we're all attending this morning. So thank you so much for having me. And if you have any questions on the insurance side, please send them through or relay them to Josh and Lewis, and I can get back to anyone.
Thank you so much, Reese.
Cheers. Thank you very much. Hope you all have a great day. Cheers. Bye.
Gentlemen, do you have to run off to the workshop as well?
No, we don't.
Well, we are, but we're very close by, so
Okay.
our commute is much shorter.
Okay, great. Let's see. Are you? I mean, it is super interesting that an insurer wanted to fund this or participate in this research to such a great extent. Are you working with other insurers to, or are they consuming these products in ways that you know about?
So currently, no, they're definitely consuming the paper that we produced, that we shared here. So that's inspired, I think it's inspired a lot of them to look along similar avenues in Australia. Obviously, this project, we have to share a lot of commercially sensitive data. So, and also there is an embargo on some of the products that we produce from this data set as well. So there's no direct sharing, of course, between competitors of Suncorp. So, but once this embargo lapses, the derived products which we produce is definitely something we could potentially share on sort of a national level to the benefit of the entire industry. So yeah, obviously, when you're working in this space, you just have to be aware there's a lot of commercial sensitivities and competition.
Sure, absolutely. Well, let's go back to this, the issue of warnings. I know you guys are not, you're meteorologists, and you probably have sort of limited connection to the, the research and whatnot about warnings. But I'm super interested in the effectiveness of warnings, and maybe how to target them in Alberta. Right? We have a sense of when the hail's coming, and we see there's a big gap between the information that meteorologists have and the message that goes out to the public. And Environment Climate Change Canada issues severe thunderstorm warnings that cover entire counties, and they say there's a big storm coming, and it could have this effect and it could have that effect, and it's not sort of less actionable than if they were able to say, hey, I understand you've got a car at 123 Main Street and there's going to be a hailstorm and it's going to drop 2-inch hailstones, so maybe you want to garage that car. Of course you probably can't issue warnings that are that specific, but you can see that there's a big gap between a big storm is coming and it could have all these different effects anywhere in this county and move your car because it's going to get whacked. Are you sort of trying to move from this side to that side?
Yeah, I think our role at the Bureau is to enable say, local governments who have a lot of information on the properties within their jurisdictions, so which one might be more vulnerable and less vulnerable. Enable electricity networks and provide distributors and also insurers. If we provide them with a rich data set, then they can use their own customer data sets to augment that data and provide more value when it reaches their targeted customers. Of course, this approach, if you're going down to an industry such as insurance, there'll be a large portion of people who aren't covered by one insurer. So you also have to be very careful relying on this approach, of course. So it's a little bit difficult for hail because it sort of doesn't really sit in Australia as a responsibility for local governments. Any messages that do go directly to customers really do come from insurers here as well. So currently they actually do take the Bureau's information in real time, do some geospatial analysis on their own exposure, their portfolio, and then send that subset of them information, the same information that the Bureau provides, but directly to those customers and provide additional advice like put your car under shelter or make safe your property. So, but yeah, there is a big gap there, and it's definitely an active area of research, particularly for social science. Not just in Australia, but everywhere across the world at the moment, trying to close that gap between what the weather agency provides and what the public actually needs and understands to act appropriately.
There's another aspect of it, especially with the vehicular side of story. I will say a large proportion of Australians do have the Bureau's weather app on their phone. And that could allow us the possibility of, once we start having the nowcasting capabilities for HDE, for saying, well, the next 30 minutes we expect there to be damaging hail in this area. There's nothing technically stopping us from potentially, since we also use the user's location to tell them weather information, there's nothing stopping it technically from having that user location, if the user location is within that swath or that damage expected damage, of having a notification on the app saying there might be hail damage on your area. If you move outside of that area, the likelihood is less. I see that as a quite viable, technically available, low-hanging fruit, basically. And it's not necessarily doing a spam message to everybody. It will be to people that have the app. They can potentially enable that feature.
So the app knows latitude and longitude down to probably meters.
Yeah, because you can give it your location to tell you your weather, which is what we usually all of us do. You can also set it up to just tell you the weather of a specific city, but
one of the options is just the app is aware of your geolocation.
Correct.
Like Google Maps is.
Yeah. That's the current app that we have. You can just set it to tell me the weather of my location.
So in principle, you could tell the app, we're expecting a hail swath in this polygon, and the app says, "Oh no, I'm in that polygon. I'd better warn my owner to move his car."
Yeah, potentially. Yeah, it's not something that is in the works, but I think that will be of high value.
Such a service does exist for the Swiss and the German weather services, so they're able to push warnings directly to customers direct to the public based on their app location.
And are they seeing success with that? I mean, are people garaging their vehicles?
I guess it's reflected in the uptake of the app as well. So there's a huge uptake in the app in those two countries, and the public, there's lots of other more interactive features in their apps as well. They engage more closely with collecting reports of what weather is going on, and they see significant benefit of having these sort of two-way interactions with the public through their app.
You said Swiss and German?
Yes.
people have these? Can you give us a proper noun? Like, is there a name for these apps?
Yeah, so it's the Meteo Swiss app, which is the weather agency in Switzerland, and it's the DWD app, their official app, which is the weather service in Germany. My German's not quite good enough to pronounce the full name of the German weather service.
Gotcha. Okay. Oh, I wanted. I'm still not getting any questions. But I have lots and lots. The hotspots. Could they? I mean, presumably, there are protection attributes that might show up like in the vehicle vulnerability. I mean, I know that we had a couple of big hailstorms in Calgary. One last year that cost 3 billion Canadian, and one just a few weeks ago that's probably in the 30-40 million dollar range. And lots of reasons for the differences, but one of the reasons for the differences is that the neighborhood that got whacked last year had people have fewer garage spaces. There's less protection for vehicles. And the one that happened a few weeks ago happened in an older neighborhood where there are more, garages per vehicle. Might that sort of thing be showing up in some of your data?
Yeah, definitely. And it also might be not only garages, but the density of parking, like commercial parking, and the density of roads, right? So they will drive that, certainly.
But the hotspots are normal cars, aren't they?
But we need to remember that this is from the observation side. From the radar side, it just telling you where there will be hail that would be damaging if there was an exposure to that, right? So,
right, got it. I was super interested in the sharp edges to the damage boundaries around slide 41. I mean, that's a really neat distinction to be able to say it's not, you don't see a smooth drop off in hail.
It's not a smooth transition. It's damaging here, and it's not damaging less here. It's just that's the. Although we did saw storms that had more of that transition, but many of the more intense ones were very sharp, delimited. Yes, and they also had relatively sharp temporal delimitations. It's not like it slowly starts to damage and then it peaks. It's more like it peaks quickly, very usually towards the center of the storm.
Right, a tap turns on, then it turns off.
Yes, it's more binary in that sense. Not completely, but it's much more than what I expected.
Interesting, super interesting. Well, we are running out of time. Do you have any last thoughts for us before I conclude the webinar?
Well, from my side, the value of having policy level data was just nothing would have been possible if we didn't have that. Also because it allows us to have nulls. Without many of the things that we have on the reports, people will report there's hail here, but nobody reports there's no hail here, because it's the problem is the survival bias, right?
Yeah.
So having the whole data set for policies allows us to also tell the model there's no hail here, so don't give us false alarms. That's extremely valuable.
Joshua?
Yeah, I guess there's one important point from my side as well. A lot of the CAP models are developed from both insurance claims and also hail size reports where they're available. And I just wanted to emphasize that there needs to be some caution around hail size reporting. It is often inferred that is the maximum hail size that is collected during the storm, but truly it is an unknown percentile in the entire distribution of hailstorm stones. The other factor is there's a huge piece of missing information when we rely on maximum hail size, and that is we don't know the concentration of hailstones. So you can have an event passing over with 15 centimeter watermelon size hailstones, but you might only get one every 100 square meters. But then you have another event with golf balls and it's producing, say, 50 per square meter, and you will have a much more significant loss event from that for property or motor. So there really just needs to be some caution about relying on hail size reports to estimate damages and loss from hailstorms.
Absolutely. Yeah. Thank you so much, gentlemen. Thank you so much. Super interesting talk, super interesting science. I want to remind our attendees, thank our attendees for coming today, and remind everybody that next month on September the 12th, CAL FIRE's Deputy Director Frank Bigelow is going to talk about California's adoption of the International Wildland Urban Interface Code and its recently released fire hazard severity maps. So that will be September 12th. Once again, remember that our speakers' slides will be available by Monday or Tuesday or so at www.iclr.org/workshops. The slides, along with the video, transcripts, and so on. So thanks, everybody, and I look forward to seeing you next month. Bye-bye.
Thank you.